This is module 3 of chapter 2. This module is devoted to the theory of nonlinear first order partial differential equation. We have already defined different type of integrals of a first order differential equation. In this module, we shall define different type of integrals taking a nonlinear equation, first order nonlinear equations, and then mainly we shall discuss the Cauchy's method of characteristic to find solution of a nonlinear first order partial differential equation. So, let us go to the first slide of this module. Suppose a nonlinear partial differential equation is given, which is written in this slide in equation number 1, where capital F is function of x, y, z, p and q. The small p is del z del x and small q is del z del y, and capital F is a nonlinear function. And we have already seen that if we start with a function which is written in equation 2 and which involve two arbitrary constants a and b, one can derive a first order partial differential equation which is written in equation number 1. So, starting from equation 2, we can go to equation 1, and conversely one can prove that the solution of a first order equation which is written in equation 1 is of the form which is written in equation 2. Now, I shall define again various type of solution of a nonlinear partial differential equation. So, we have seen in our first slide that equation 2 is a solution of 1 involving two arbitrary constants a and b. So, this solution is called complete integral of equation 1. Suppose there exists a relation between the parameters a and b of the form b is some function of a which is psi a, psi being arbitrary, then if x, y, z a psi a equals to 0 is also a solution of the given equation, and the envelope of this one parameter system constitute a solution of the given equation 1, and that solution is known as general integral of equation 1. There is another type of integral which is known as singular integral, and it can be obtained by considering the envelope of the two parameter system of surfaces 2. So, if we calculate or evaluate the envelope of two parameter system of surfaces 2, that solution will give a singular solution of the equation 1. Now, we shall take one equation, one example to explain all type of solutions. So, in this example, the equation is given z equals to px plus qy plus p plus q minus pq. We have to show that the solution of this equation is z equals to ax plus by plus a plus b minus ab, and which is complete integral of the given equation. And we have to show that envelope of all planes corresponding to complete integrals provided singular integral of the differential equation, and we have to determine the general integral by find the envelope of these planes, and which also passes through origin. Now, we write the function f which is the general integral in the form f x y z a b as z minus a x plus b y plus a plus b minus a b equals to 0. So, here we can observe that value of p in this solution is constant. That means, we can obtain the complete integral by substituting p as a and q as b, and therefore, the solution x y z a b is equal to 0 is a complete integral of the equation z equals to px plus qy plus P plus Q minus PQ. Now, the envelope of these two parameter system will give the singular solution of the given equation. So, to obtain the singular solution, we solve the equation f equals to 0, del f del a equals to 0 and del f del b equals to 0. So, if we write the equations, it will be in this form. The first equation corresponds to f equals to 0 and the second equation corresponds to del f del a equals to 0 and the third equation corresponds to del f del b equals to 0. So, from last two equation one can obtain the values of a and b easily, and if we substitute the values of a and b in the first equation, we will get z as function of x y, which is written here as x plus 1 into y plus 1, and this solution is the singular solution of the given equation. Now, we want to find a general integral of the given equation. To find general integral, suppose a and b are related by the relation b is equal to psi a. Now, from f equals to 0, if we put the value of b as psi a, we obtain a relation which is written in the slide, and to find the general integral, we have to find the envelope of the one parameter system which is written here. So, to obtain the envelope of one parameter system where a is the parameter, we have to solve f equals to 0 together with del f del a equals to 0. The expression for del f del a is written here. So, now we have to solve f equals to 0, del f del a equals to 0, and we have to find that integral which passes through origin. So, in the previous expression, in the expression for f, we substitute x equals to 0, y equals to 0 and z equals to 0. Since the integral passes through origin, we get a relation minus a minus psi a plus a psi a equals to 0, which gives the expression for psi a as a by a minus 1, and we can immediately find the value of psi dash a as minus 1 by a minus 1 whole square. Now, we have another equation del f del a equals to 0. So, in del f del a equals to 0, if we substitute the values of psi a and psi dash a, we can obtain a relation which is written here, and from that equation we can find the value of a as square root of y by x plus 1. So, taking this value of a, we can write down the functional form of psi as root y plus root x by root y. Now, in the expression f equals to 0, if we substitute in the expression f equals to 0, if we substitute the values of a and psi a, we obtain a function z equals to root y root x by root y into x plus root y root x by root y into y and so on, which is written here. So, after simplification, we get equation of the integral surface, or the general integral is x plus y minus z whole square equals to 4xy. So, this is our general integral. So, in this example, we calculate the complete integral, singular integral and the general integral. Now, I am going to explain Cauchy's method of characteristic to find complete integral of a given nonlinear first order differential equation. This method is based on a geometrical idea. First of all, we shall derive the Cauchy's characteristic equations, then using that concept we shall find general integral of a nonlinear equation passing through a given curve. So, let us go to the slide show of the Cauchy's characteristic equation. before describing Cauchy's method of characteristic, I will give some definition of some elementary things. Suppose there is a point P having coordinates x0, y0, z0 and we want to draw a plane through the point P. So, one can draw infinite number of planes passing through point P. So, to uniquely specify a plane, we need the direction ratios of the normal to the plane. Let us fix that direction at in the direction n, which has the components P0, Q0 minus 1. Therefore, a set of 5 numbers x0, y0, z0, p0, q0 always define a unique plane. So, the set x0, y0, z0, p0, q0 is called the plane element in the space. Suppose a plane element x0, y0, z0, p0, q0 satisfy the equation 1. That means equation 1 is the given partial first order differential equation. So, then the plane element is called the integral element, and the equation in equation 1 we have small f, capital F x, y, z, p, q equals to 0, and from that equation we can obtain the value of q as some function of p, which is written in equation 3, and suppose that function is g. Now, if we fix the point x, y, z and vary the point p, we will get a set of plane elements in the form x0, y0, z0, p, g, x0, y0, z0, p. That means the set of elements are such that all the planes passes through the fixed point x0, y0, z0, but the direction of the normal are different for the different planes. Therefore, this set of planes envelop a cone and all this cone passes through the fixed point P, and this cone is known as elementary cone of the given equation 1 at the point P. The picture of that elementary cone is shown here. So, P is our fixed point and a particular position of the plane element is given here, and n is the normal to the plane. Now, consider a surface S having equation z equals to gxy, where the function gxy and its first order partial derivatives with respect to x and y are continuous in some defined region capital omega in xy plane. Then the tangent plane at every point of S determines a plane element of the type x0, y0, gx0, y0, gx x0, y0 and gy x0, y0, and this is called tangent element of the surface S at the point x0, y0, gx0, y0. So, using this concept, we can write the important theorem, or we can state the important theorem as which is written here: a necessary and sufficient condition for a surface to be an integral surface of a partial differential equation is that at each point its tangent element should touch the elementary cone. Now, we want to derive Cauchy's characteristic equations. To derive that equation, we first consider there is a curve gamma, the equation of which curve is given in parametric form, where t is the parameter. So, x is some function of t, y is some function of t and z is also some function of t, and which lies on the surface S. Therefore, it will satisfy the equation of the surface. So, z equals to g x t y t for all t belongs to some interval I. then if P0 is a point on gamma determined by the parameter T0, then the direction ratios of the tangent line P0, P1 are x dash T0, y dash T0, z dash T0, where dash denote the derivative with respect to t at the point t equals to 0, T0. The picture of this is given in figure 2, where PP0 is the tangent line to the curve gamma. Now, the direction P0 Q0 minus 1 is perpendicular to x dash y dash z dash. Therefore, P0 x dash plus Q0 y dash plus minus 1 z dash equals to 0. So, from this equation one can write the value of z dash as z dash equals to P0 x dash plus Q0 y dash. Thus, any set xt, yt, zt, pt, qt satisfying z dash t equals to pt x dash t plus qt y dash t defines a strip at the point x, y, z of the curve gamma, as it is shown in figure 2. If such a strip is an integral element of the equation 1, equation 1 means the equation capital F x, y, z, p, q equals to 0, then that strip is called the integral strip of the given equation. Thus, the set of functions x, y, z, p, t is an integral strip if it satisfies the condition 6 and the condition f x, y, z, p, q equals to 0 for all t belongs to I. Now, we are in the position of finding solution of a Cauchy problem. If at each point the curve gamma touches a generator of elementary cone, then the corresponding strip is called characteristic strip. So, let there is a point neighboring to the point x, y, z and having coordinates x plus dx, y plus dy, z plus dz. It lies on the tangent plane to the elementary cone, then dz must be equals to p dx plus q dy, where p, q satisfy the equation 1. Equation 1 means the given equation. Now, from equation 1, if we take derivative with respect to p, we get del f del p plus del f del q dq dp equals to 0. And from equation 8, if we differentiate the equation with respect to p, we get dx plus dq dp dy equals to 0. Now, if we eliminate dq dp from the two equations which is written in 9. So, eliminating dq dp or putting the value of dq dp from the first equation to the second, we can get a relation between dx and dy. Now, the equation 8 and 9 are compatible. So, from 8 and 9 we can derive that dx, dy and dz are proportional to fp, fq and pfp plus qfq respectively along the characteristic strip. Now, we choose the parameter t in such a way that x dash t equals to fp, y dash t equals to fq and z dash t equals to pfp plus qfq. So, along the characteristic strip, p is also function of the parameter t, and that function can be obtained in this way. If you take p dash t, compute p dash t, it is del p del x dx dt plus del p del y dy dt. Now, substituting the values of x dash t and y dash t, we get this equals to del p del x del f del p plus del P del Y del F del Q. Now, the value of del Q del X is equals to the value of del P del Y, which is proved here. The value of del P del Y can be written as del 2z del Y del X. Now, if we interchange the order of the derivative, we get del 2z, this equals to del 2z del X del Y, and which is nothing but del Q del X. So, in the previous equation we have used the relation del P del Y equals to del Q del X. Thus, we obtain the value of P dash T is this. Now, if we substitute, now if we differentiate equation number 7 with respect to x, equation number 7 means the given equation, differential equation P, which is where all the variables x, y, z, p, q are function of t. So, if we differentiate equation number 7, we will get with respect to x, we will get a relation in this form, and here if we use the relation, if we use the value of P dash T as del F del P del X plus del F del Q del X, we obtain a relation, or rather we can find the value of P dash T as minus of Fx plus P Fz. In the similar way, we can find the value of Q dash T as minus of Fy plus Q Fz. Now, we can find the differential equations for all the 5 variables x, y, z, p and q, which are written in equation number 11. And this equation is known as Cauchy's characteristic equations. And there is an important theorem which says that if a characteristic strip contains at least one integral element of f x pq equals to 0, then it is an integral strip of this equation. Now, we are interested to find the integral of a given equation, nonlinear equation, which passes through a given curve gamma. Thus, we are interested to find the solution of capital F equals to 0 and which passes through gamma, and the equation of gamma is written in parametric form. Small x is some function of zeta, y is some function of zeta and z is some function of zeta. And we know that for a given equation we can find Cauchy's characteristic equation, which is set of 5 ordinary first order differential equation, which is written in 11, equation number 11. So, solution of that equation is of the type x is some function of x0, y0, z0, p0, q0, q0, t0, t. Similarly, all variables y, z, p, q, they are functions of x0, y0, z0, p0, q0, t0 and t, where x0 is some initial value of x, which for this case we are taking the given value of x from the curve which passes through the curve gamma. So, x0 is taken as phi zeta, y0 as psi zeta and z0 as chi zeta. So, the corresponding value of p0 q0 can be obtained in this way: dz equals to p0 dx plus q0 dy, and z is function of chi zeta. So, dz, so if you take derivative, so chi dash zeta equals to p0 phi dash zeta plus q0 psi dash zeta. So, we have a relation between, linear relation between p0 and q0 in the first equation, and we also have capital F, which is function of phi, psi, chi, p0, q0 equals to 0. So, solving these two equations, we can find the values of p0 and q0. Therefore, all the variables x, y, z, p, q are known in terms of x0, y0, z0, p0, q0 and t0. So, x, y and z, they are function of only xi and t. So, there are three relations between xi and t. So, among these three relations, we can eliminate xi and t to obtain a functional form between x, y and z, theta x, y, z equals to 0, which is written in equation number 14. So, this is our required general integral passing through the given curve gamma, the equation of which is known. Now, we shall take one example to make the concept more clear. So, take this example, we have to find the characteristic of the equation PQ equals to Z, and we have to determine the integral surface which passes through the parabola x equals to 0, y square equals to z. So, here capital F, that means the given equation is PQ minus Z equals to 0, and we can immediately write down the corresponding Cauchy's characteristic equation, which is written here, x dash t equals to Fp, for this case it is capital Q, y dash t equals to P and z dash t equals to 2pq, and p dash t is P, q dash t is Q. The equation of the given curve is x equals to 0, y square equals to z. So, our initial condition is x0 equals to 0, y0 equals to zeta and z0 equals to zeta square. So, this is parametric form of the given curve. Now, using this relation z0 dash equals to p0 x0 dash plus q0 y0 dash, if we substitute the values of this, z0 dash is 2 zeta and x0 dash is 0. So, we can obtain the value y0 dash is 1. So, substituting these values, we can find the value of q0 as 2 zeta, and we have also the given equation pq equals to z. So, putting the values of p0, q0 in the given equation, we can obtain the value of p0 as zeta by 2. Now, we have 5 equations, x dash t equals to q, q dash t equals to q and x. So, from these two equations we can find a relation between x and q as x equals to q plus c1, and also y dash equals to p, p dash equals to p. We obtain a relation y is equal to p plus c2, where c1, c2 are constants. So, using the initial conditions, one can obtain a relation between x and q as x equals to q minus 2 zeta and y is equal to p plus zeta by 2. But in this equation we also have p0 t equals to p and q dash equals to q. So, it gives p as c3 e to the power t, and after integrating we similarly get q is equal to c4 e to the power t, and the values of c3, c4 can be obtained using the initial value. So, these values becomes zeta by 2 and c4 2 zeta. So, we get the value of p as zeta by 2 e to the power t and value of q as 2 zeta e to the power t. So, we get x is some function of x and zeta, y is also some function of x and zeta. So, from these two equations we can find value of e to the power t, which is written here, and value of zeta, which is some function of x and y, which is also written here. But we need to apply the differential equation for z, which is z dash t equals to 2pq. So, if you substitute the values of p and q, and after integrating we get z equals to zeta square e to the power 2t where we have used the initial condition z0 equals to zeta square at t equals to 0. Now, in this expression, if we substitute the value of zeta and e to the power t from the previous slide, we obtain z as some function of x and y, which is written here 16z equals to x plus 4y whole square. So, this is our required integral. So, this is our required integral which passes through the given parabola, and the equation x equals to 2 zeta e to the power t minus 1, y is equal to zeta by 2 e to the power t plus 1, and z equals to zeta square e to the power 2. These are the Cauchy's characteristic curve. We know that a nonlinear partial differential equation is very difficult to solve compared to a linear and quasi-linear differential equation. In this module, we have discussed a geometrical way to solve a nonlinear partial first order differential equation, which is known as Cauchy's method of characteristic. So, it is very useful to find solution of any type of first order partial differential equation.